Okay, so we've talked about the expectation of our estimators, our OLS estimators in multiple regression. We talked about under those assumptions 1 to 4 that we get unbiased estimators. We then looked at what happened when we included an irrelevant variable and saw had no effect on unbiasedness, but as we're going to see in a second, might affect the variance. And then we saw what happens when we leave out an important variable outside of our regression, and we saw that it causes a bias in our estimators. Unless there's kind of no correlation between that variable we left out and the variable we're interested in, or if that variable we left out actually is irrelevant because it has no effect on y. Now we can talk about the variance of our OLS estimators. And we're not going to derive them all like we did in simple regression, but we'll write out the assumptions, we'll write an expression for this variance and talk about different factors that are affecting this variance in this expression. So let's talk about the variance of our OLS estimators in multiple regression. So we're going to have assumptions that we're going to use now are, again, linear in parameters. Linear and, I'm going to get lazy here, parameters. 2, random sampling. 3, remember that new one, no perfect multicollinearity. So one of your x's can't be a linear combination of the other. Multicollinearity. The 4th one, remember, is this big assumption, expectation of u given now all of the x's equals 0. So the error term is now mean independent of all the x's. This is what was failing that was giving us that bias. We looked at the simple case of omitted variable bias. Now we're going to add that 5th assumption that we've talked about before, and that's homoscedasticity. So this is the idea, remember, that the variance of u given x, and let's say, maybe I should make it clear that it's all the x's. It's the variance of u given x1, x2, all the x's, xk, equals a constant. So remember we talked about that, this assumption when we talked about the variance for the simple case, and we needed that to do this step where we derive the variance to get a nicer expression. And so we know it's homoscedastic if there's no I subscript there to tell us that different levels of u are going to have different variances. So under these assumptions, the variance of beta hat j is equal to sigma squared over SSTJ 1 minus r squared j. So that looks like it probably came out of nowhere, but we're not going to derive it, and instead we're just going to concentrate on these 3 different aspects of it. So 1, 2, and 3. We're going to think of those 3 parts of this formula to talk about what's affecting if this variance of our estimator is large or small. And we're just looking at, one of these, the variances of one of these betas. It could be the variance for any of, x1, x2, whichever one, xk. Okay, so let's talk about each of these 3 components of this variance so we know what they mean and when they're going to be kind of big or small and how that affects this variance. So let's just rewrite the formula for our variance. Up here, the variance of beta hat j is sigma squared over SSTJ 1 minus r squared j, and these terms are probably a little bit confusing, but we're going to talk about them one at a time. So 1, 2, and then 3. So let's talk about this first term here, this sigma squared. So remember, this sigma squared is the variance of u, like we just talked about. That's how we just defined it, right? So the larger sigma squared, because it's on the numerator, the larger sigma squared, the larger the variance. Of our OLS estimators. I mean, the idea here is that kind of more noise, so the bigger the variance in U, the harder it is to kind of pin down our estimator. There's not much we can do to reduce it. I mean, it's kind of just what it is, right? But one way to reduce it is adding more variables. I mean, relevant variables, I guess, would be key here. Adding variables which are going to kind of reduce the noise in our regression. So that's the first component. So it's on the numerator. The bigger the numerator, the bigger the variance. We want the variance to be small, right? And so one way of kind of reducing the variance is to add more variables that are explaining explaining our y. Now let's move on to what SSTJ is going to be. So let's just write that down. At the bottom here, we can fit it in. So SSTJ is going to be the sample variation in whatever of whatever x that this beta j is attached to. So in this case, that's xj, right? So it's going to be the sample variation in xj. Whatever variable we're calculating the variance of that estimator for, right? And so this is the idea that we'd want lots of variation in our x. So if we had two choices, I can even just draw a really simple example right here. This is our xj values, and this is our y values or whatever. If we have all of our sample kind of clumped up like this, our variance might be bigger than if we had lots of spread out values of xj. In a situation like this bottom plane, Cartesian plane, this is going to be a larger number. So this is the idea that we want more variation in whatever variable we're trying to get the effect of. Where if it's all clumped together, then it's going to be really hard to keep this variance of our estimator small. Okay, so let's erase this and we'll talk about this final component. And this is kind of gets back to like when I talked about that adding irrelevant variables and how that might affect the variance of our estimators. It doesn't affect unbiasedness, but it might affect the variance. And it's going to come through this last term, the 1 minus r squared j. So let's erase this board and talk about that last component. So this third term we're talking about has to do with this r squared j. So let's first define what this r squared j is, where it's going to be the r squared. So remember, that's SS, or explained sum of squares over the total sum of squares. But from a different regression, from a regression where we have xj, I should say, as our dependent variable, and then we have all the other x's as our independent variable. So x1, alpha 2, x2, plus all of them alpha k, xk, for all k not equal to j. So all I'm trying to say with this terrible math notation is that this r squared j is the r squared from a regression where xj, so whatever variable we're getting the variance of the partial effect from, where this xj is our dependent variable and all the other x's in our regression are independent variables. Think of this as kind of capturing correlation between xj and other independent variables. So it's capturing this correlation. And remember, that's going to be between 0 and 1. Our r squared is always going to be between 0 and 1. So again, this r squared j is not the r squared from our regression y equals x1, y equals beta 0 plus x1, beta 1 plus blah, 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 blah. It's using this xj as our dependent variable. And again, it's between 0 and 1. And the more correlated our xj is with the other variables, the closer this r squared j is going to be to 1. And notice the closer this gets to 1, the larger this variance is, because we're starting to divide by a number closer and closer to 0. And so if we write out a little graph of kind of what's happening. So here's our variance of beta hat j on the y-axis there. And this is r squared j, or the correlation between them. Remember, they can't be perfectly correlated, or other we'd have perfect multicollinearity and we couldn't estimate it. But there's going to be some, let's say there's, the most it can be is 1. And as this variance between these, as the correlation between these two, between our xj and the other independent variables increases, the variance is just going to start to blow up. It's going to approach infinity in the limit, right? We're never actually going to get to 1 because we couldn't run the regression because we'd have perfect multicollinearity. But it has this relationship. And so this is the problem when you start adding those irrelevant variables, is if they're correlated with xj, we're increasing the variance of our estimators for no reason. So we shouldn't just throw every variable in the kitchen sink in our regression. We need to think about what to include and what not to include.